So last time we started to introduce the Hatree-Fock theory, which is a perturbative approach to cooling interacting electron gas. And such a system with a Hamiltonian given by this H0 plus electron-electron Coulomb potential, and this phi 0 is the many-body ground state of H0 Hamiltonian. Okay? Whereas epsilon 0 is the eigenvalue of such a H0 system. And remember, this epsilon 0 could be calculated quite easily, which is given by this number. And it was assigned to you as a homework. So the logic behind this Hatree-Fock theory is this Hamiltonian is given by this H, and this phi is the exact eigenstate of the H Hamiltonian, which is unknown. Okay, so this is the true eigenstate is unknown, and also we cannot know the exact eigenstate because we cannot solve the, as mentioned many times, the the Schrödinger equation for such millions and millions particles. So what can we do is that we make approximations because we know this exact eigenstate of H0. So we start from this as unperturbed eigenstate of the system. We treat this V as a small perturbation. And I mentioned last time that this V is not small. Therefore, this kind of approach, fails. Okay, but before we actually know how to more accurately capture this physics, let's just follow the Hatree-Fock. Therefore, the eigenenergy of the full Hamiltonian is approximately given by this Hatree-Fock measure element, which is simply just expression value of this operator H sandwiched by phi 0 instead of phi, because we don't know what this phi is, but we know what this phi 0 is. Okay, so that's the starting point of the Hatree-Fock. So the first term has been done already last time, right? So this H0 sandwiched by phi 0 is given by epsilon 0, which is this. So now we are evaluating this, the second part, which is more interesting, which is the expression value of the potential energy. Okay, sandwiched by this phi 0, unperturbed eigenstate of the H0. Right, so if I expand this, operator formulation of this V, and it is given by this Coulomb scattering processes, as I mentioned many times, that there are two electrons come in and they are destroyed and they are scattered by the Coulomb, and after scattering there are two electrons generated carrying different momentum, k minus q and k prime plus q. Okay, so there's a momentum transfer of amount of q goes from this initial state k to the initial state k prime, so that this particle is actually carrying momentum minus q, and in addition to this k, and this particle carry additional momentum q. So how do we evaluate this measure element? We need to take advantage of this orthogonal and normalized condition. So there, remember, this phi 0 contains product of the n single particle creation operator, and this is what V, and so we are calculating this measure element, sandwich in between this V is the product of the n single particle creation operator. Okay, so remember there are four operators in this V operator, and two creation and two destruction. So we need to destroy two electrons out of this n single particle eigenstate of H0, and then we need to create another two particles as a final state. But we could do it this way, so we destroy these two particles on the right, and then we also do it reversely, that we destroy these two particles of this, I should say, the broad state, or the Hermitian conjugate of the initial state, which is the final state. So at the end of the day, we will destroy two particles and create another two. So you'll see that the final result for this matrix element will have such a form like this. So in order to actually match this, say, initial and final state, so the final state and initial state must be the same. So let me just tell you why. Because of this orthogonal condition of phi and phi. Okay, so let me re-express this matrix element in a more transparent way so that you will see this is the natural result. Okay, so the occupation number is actually conserved. So when we actually destroy this C3 and C4, so remember there may be some creation operator somewhere here, so that you need to actually destroy them so that the Ki or Ki plus 1, so the momentum of Ki and Ki plus 1 should match this 3 and 4, which stands for K prime and K, and so on and so forth. So you will have another operator here, Kj, J, or Ki prime and Kj prime. Okay, so that you also destroy these two particles, and so that this momentum will be matched. Otherwise, you don't get the finite result because the particle number on the left hand side should be identical to the particle number on the right hand side, and therefore you need to exactly match the momentum of the initial particle that you want to destroy it and also this final state. Therefore, we need to exactly match this momentum of the initial state and final state. So, in other words, the momentum K can be identified with this K minus Q and K prime with K prime plus Q. Or we could do it reversely, that the K should be identified with K prime plus Q and K prime with K minus Q. So let me write it here. So there are two possibilities. Number one, K is same as K minus Q, and K prime is K prime plus Q. And possibility number two is the other way around, that K prime plus Q is K and K minus Q is actually K prime. So let me just illustrate how it works. The easiest option is when Q is 0, actually when Q is 0, so let me just, we erase the blackboard and we could continue with the calculation. So the important lesson is that when this Bronsted cascade contains different number of particles and they are orthogonal to each other, okay? And that's why you need to guarantee that these initial states match the final state momentum. So I will illustrate how that works. So let's just take this, the simplest possibility we can imagine, where this momentum transfer is 0. This is called the direct term, that the two electrons do not change their momentum during the scattering, which means that the photon or the Coulomb potential actually carry 0 momentum transfer. Okay, suppose Q is 0, then this incoming electrons can K prime. They simply just pass by this scattering center, and the momentum still remain the same. Okay, so let's just verify that this indeed gives us some finite results. So let's just try to destroy two particles. Suppose there's there K2. Suppose this C dagger K1 and C dagger K2 could be the two electron states carry K and K prime. So of course these two electrons could be chosen arbitrarily as you like. So suppose I choose this two to be destroyed, so that you could simply just rewrite everything. If you remember the occupation number representation of this many body wave function, and this is simply like this, right? So suppose this K1 is actually K prime and K2 is actually K, and you can very easily just do the algebra by the definition of a destruction operator. So suppose I destroy this, so I get -1 to the power of, say, 1. So of course K2 is actually K. And then I could just destroy this K1 particle one more time. So this is what, -1 to the power of what? There's no particle on the left-hand side of this K1 particle. So this is actually -1 to the power of 0. And then this is, and K1 is actually K prime 0. K2 is actually K, which is 0. So now I destroy these two particles, K1 and K2, and assuming that this, say, K1 is actually K prime and K2 is K. Okay, so now I should create these two particles one more time. So I just don't change this operator on the left-hand side, but only consider this, which is -1, where there's no particles, stay K prime and stay K. So now I create these two particles, and this is given by, again, if I create this, I get -1 power of 0 because there's no particle on the left-hand side of this K prime particle. So I can very easily create this, and I can also create this. And in that case, I have one particle on the left-hand side of the particle K. So this is -1, one more factor -1. So nk prime is 1, nk is 1. But remember, the left-hand side actually should be identical to the Dirac cascade on the right. The reason is that this can be rewritten in terms of those occupations, and nk1, nk2, and so on and so forth. And -1 is actually +1, and nk prime is 1, and nk is 1, Right? As I've just assigned over here that K1 is actually K prime and K2 is actually K, and therefore this matrix element gives you 1. However, if you do not have such a identification or match between initial and final state momentum, then you're going to have different states on the left compared to the state on the right, which is 0, and this is when the initial and the final state are not identical. All right, so you could verify this. Okay, so if you don't match this initial and final state momentum, and the consequence of that is that when you actually operate this two creation, two destruction operators on any of this Dirac-Brown or cascade, and you will find that the Brown cascades are orthogonal to each other because they don't match the initial and final state momentum, right? So that's because of this orthonormal conditions of the eigenbasis phi 0, and therefore we must respect the match of this initial and final state momentum. So you could verify by yourself at home that if I just arbitrarily assign this full momentum without matching them, then you're getting this vanishing of the matrix elements at the end of the day. So then we simply just consider this as just a theorem, or the condition that must be obeyed, and so let's just take this for granted. And let me just describe these two possibilities of matching this initial and final state momentum one more time. So the first choice is when we have 0 momentum transfer. As I mentioned, this is a direct scattering processes, and which we call this Hatree term, or the direct term. And this term is actually given by matrix element, which is 1, and times this V0, right? which means that the result of this direct term is given by this Q0 component of the Fourier transform of the potential, Coulomb potential, which is infinity, as you know that, and which we don't care because of the charge neutrality condition, right? Because the system is charge neutral, so that all this Q equals 0 component of the V of Q could be considered as just a part of this, charge neutrality, right? So it's just a part of the story. So if you sum over all such a Q equals 0 component of all Coulomb term, and you'll get 0. Therefore, we don't take this term into account because it will be cancelled by charge neutral condition of the system. Is that clear? Good. So then we take a short break, and when we come back, we will continue discussing the second so-called exchange processes, or the Fock term, and which leads to the new result. This algebra is very straightforward, but I think it's very necessary to convince you that the momentum carried by initial and final state should be matched. Otherwise, you get orthogonal between the Dirac-Brock state and Cat states. Okay, so let's look at the other possibility, which is called the exchange term, or the Fock term. And in this case, this K prime plus Q as a final state momentum is identified with the initial state K, and vice versa, this K minus Q state of the final state is actually the same as K prime as initial state, which means that the two initial states are exchanged after the scattering, because the electron carries momentum K as initial state. When it actually comes out, it carries K prime, which is exactly the momentum carried by the other electron, right? And vice versa. So the electron carry K prime as their momentum initially. After scattering, it changes to K, which is precisely the initial momentum for the other electron. Okay, so in other words, these two electrons actually exchange their momentum after the Coulomb scattering. So you could visualize this called exchange processes, or the Fock term, from this kind of a diagram where this circle represents the Fermi surface or Fermi sphere. There are electrons which are active. Remember, there are two thin shells within and the out of the Fermi sphere where electrons can actually form quasi-particles. So suppose there's an electron here, carry momentum K, and another electron over there, carry K prime. They could actually interact by Coulomb, and they exchange their momentum. All right, so the electron state K is here, and K prime is there, and they interact by Coulomb. After scattering, this electron here, carrying momentum K, is actually moving to the states with K prime, and K prime moves to K. Okay, so they exchange their momentum. Okay, of course, these two electron states could be any arbitrary states within or out of the Fermi surface, within the range of the KBT. So whenever there are two electrons within these two thin shells, and they could interact by Coulomb, and the second term that we call this exchange or Fock term tells you that these two electrons actually get exchanged, and their momentum are exchanged, and their spins are exchanged. The sigma after scattering becomes sigma prime, and the sigma prime here becomes sigma after scattering. But then the sigma should be equal to the sigma prime because the spin is actually conserved. So we have a spin conservation because there is no other, say, interactions which will flip the spin, and therefore the initial and final state spin configurations must be the same, right? Okay, and therefore this exchange term occurs only when these two electrons, initial states and final states, are having the same spin configurations. For example, this can only lead to two processes if we include the spin. So this K would spin up, and K prime would spin up, K prime would spin up, and K spin up. Or the other way around, all the spins are pointing down. You see all this, either all the 4 spins are pointing up like this or pointing down like that. Okay, because the spin must be conserved at the interaction vortex, and the reason is that there's no reason that the spins will get flipped, okay, by any other interaction, because there's no other interactions which will flip the spin. So there's no spin dependent coupling here. The only interaction here is actually the Coulomb potential. Okay, so the Coulomb potential in this process cannot change the spin orientation of the electron. So even though their momentum got exchanged, their spins do not exchange. And this is a very important result coming from the Hatree-Fock, and which leads to almost ferromagnetic ordering in many metals, which overestimates the tendencies towards the ferromagnetism in solid state, which is of course wrong. Okay, so there are different spin interactions in this Coulomb scattering, and it's just that this Hatree-Fock approximation neglect all such interactions among different spin species. So you immediately see something wrong here when we only care about this, say, exchange term when the spin species are conserved. Or you can consider only the processes that involve the same spin species. Okay, of course, you know that when you talk about these Coulomb interactions, because the electrons carry spins with spin up and spin down, how come this spin up electrons does not couple to the spin down electrons? Of course, there's a coupling between upspin and downspin electrons by Coulomb, but it doesn't show up here. Of course, Coulomb interactions connect, couple electrons with both same or opposite spin. Okay, so it's just the Hatree-Fock cannot capture that physics. Okay, so without going to details, you immediately notice something's wrong with the Hatree-Fock, because this part of the interaction between different species is missing. Nevertheless, we simply just follow what Hatree-Fock predicted, and let's just calculate this. And let me just finish this, the Fock term, plus sum over q, k, k prime, and so on. And so let's just plug in this exchange conditions of the second term, the Mr. Fock term. So there are 2 initial states with momentum k prime and k, and 2 final states carrying the the exchange momentum. But how do we carry out this calculation? Well, this is straightforward, because as I mentioned this many times, the advantage of presenting this many-body states in the second quantization formulation is that we could convert all these operators into what? The number operator, right? It is a function of number operator. The number operator, when you take the expression value and 0 temperature or any finite temperature, it is a function of the Fermi function. So everything now becomes a function of the Fermi function, and which is easy to calculate. So let's just finish the job. So we could take advantage of this anti-commutation rules, and k prime is actually delta k prime. And we could simply rewrite this for fermion term, ck prime, c dagger k, c of k. All right? So we could simply just exchange these 2 operators, c dagger k and ck prime, and using this anti-commutation rules over here, and so that these 2 operators becomes that thing over here. So let me just focus on the operator part of this second term, and we could just put all those Coulomb interactions at the final stage. All right, so everyone agrees, nothing mysterious. So then we could just rewrite this, expand these 2 terms. delta k prime, and c k minus prime, c k prime, c delta k, c k 0. You simply just separate this term from that term, and you get the first term with the c dagger c and the delta function, delta k prime, with the minus sign here, followed by the second term, c dagger k prime, ck prime, and c dagger k, ck. So tell me what this is. Tell me what this is. I need a volunteer to actually mark this term in terms of the occupation number. And you make a circle. Within the circle, it is the number operator. Okay, so let me do it this time, but next time it's your job. So what about this? What about this? You see that? This is what nk wearing a hat. This is nk prime wearing a hat. Yes? So these two are the number operators, which reports to you the number of particles in that state as an eigenvalue. And if you use this number operators, sandwich in between here, this phi 0 on the left and phi 0 on the right, and you will get the number of particles that stay in momentum k and k prime. So as simple as that. So let me just finish this, the first term. Well, again, you remember there's a summation over k and k prime, right? So there's a delta function. This is a Kronecker delta function, which gives you 1 when k is equal to k prime and 0 when they are not the same. Okay, so this is simply just what? Sum over k, because I sum over k prime and taking advantage of this delta function, so I get c dagger k and ck. Okay, but the summation over k and k prime applies to both terms. The first term gives you exactly the stuff like this one, which is the number operator nk hat, and the second term, which is sum over k and k prime and k and k prime. Of course, you can interchange the order of nk and nk prime because they commute. So you could very easily see that nk hat and k prime hat is the same as nk prime hat n of k. All right, and then I should close this Nash's element. So now you know how to do this calculation because, say, the first term is nothing but expectation value of nk, right? What is this? Well, this is nothing but simply just you sum over all the particle number, which is total number of electrons. Okay, so now the Fock term becomes this one, right? So you got number operator for the first term nk and the product of the two number operators nk and nk prime for the second term with a minus sign, and you sandwich this by phi 0 phi 0. Sorry, this is entirely correct. Minus nk prime and phi 0. This is the first term, and this is the second term. So the first term is this k minus k prime, which is q, n of k and delta kk prime. Since there's a delta function here, which vanishes when k is not the same as k prime, so this term survives only if k is the same as k prime, which means that this is nothing but the sum of all Coulomb potential, right? Q equals 0 component of a V of Q, and this is n of k, and you sum over k. Okay, so again, this is nothing but just infinity that we mentioned many, many times. So this is infinity, but it can be cancelled by charge neutral. So we don't care about this. So let's just consider the second term. The second term is this with a minus sign, and k prime. The second term is sum over k and k prime. So you will have the term when k is same as k prime, and you will also have the term that k is not the same as k prime. right? Okay, so the second term is this summation over k and k prime of this Coulomb potential and multiplied by the product of the two, say, occupation number operator, nk and k prime. But in general, k can be equal to or not equal to k prime. So we need to separate these two cases. The first case is, again, the case where k is the same as k prime, and therefore this simply just counts the number of pairs of electrons and multiplied by this Q0 components of Coulomb potential in Fourier space, which is the sum over all this Coulomb energy. And again, this gives you infinity, and that infinity, we don't care, because we know that by this charge neutrality condition, all this plus or minus infinity will be cancelled out, and you don't have such an infinity anymore if you count all these divergent contributions from the Coulomb potential at Q equals 0. So at the end of the day, you get only this non-trivial contributions, which is sum over k and k prime of the Coulomb potential, which is function of the difference between k and k prime vector, and times this two Fermi functions, which is a theta function. At t equals 0, this is simply just Fermi functions. Well, at finite temperature, it also gives you the Fermi function when you really evaluate this, this matrix element sandwiched by this phi 0 state, right? Okay, so at 0 temperature, this Fermi function reduces to the theta function. It is a step function. So remember, we plot this many, many times, that an f as function of momentum of energy shows such a jump. And within the Fermi sphere, you get occupation fully occupied state, where this nf is 1. And beyond this, above this kf, you get 0 occupation. And this mathematically could be represented by a theta function, where this is kf minus k. Kf minus k. This is 1 if k is less than kf, and 0 if k is greater than kf. So, which means that the theta of x is 1 if x is positive, and 0 if x is negative. All right? So now I simply just rewrite this k prime as k plus q, because this is precisely this momentum transfer is telling us. So now we need to evaluate this thing, which is a bit troublesome, because this is the Coulomb potential in terms of k minus k prime in the denominator with absolute value and multiplied by this 2 theta function. Okay, so what is this strange thing? Well, of course, it's not strange at all, because you could evaluate this pretty straightforwardly by simply considering the intersection volume between two Fermi spheres. This is, again, given by this epsilon 2, which is the Fock energy, per particle, which is this minus volume number of electrons, sum over k prime, and sigma prime, 2 pi e squared, k minus k prime squared. And of course, you need to sum over the spins, where sigma is actually the same as sigma prime. So meaning you have only two terms, whether the force spins are up or all pointing down. Only these two cases. So of course, you need to multiply by these 2 theta functions, kf minus k and kf minus k plus q. Okay, so you could more straightforwardly calculate this term, this summation, if you consider the 2 Fermi spheres. And one of them represents the theta function, the Fermi function with momentum k. Another represents this Fermi function at different momentum k prime. Remember, when you multiply these two number operator, or in terms of the Fermi function after this evaluation of the matrix element, you'll see that the non-zero contribution is only coming from the intersection of these two spheres. Why? Because remember, in this Fermi sphere at 0 temperature, this NF is actually 1 inside the Fermi sphere, and NF is actually 0 outside of the Fermi sphere, right? Suppose I simply just use blue lines to shade this Fermi sphere. Within this KF regime, you get fully occupied, and you get fully empty out of this sphere. It's the same for the second Fermi sphere. So the second Fermi sphere is actually 1 inside this orange sphere and 0 out of the sphere. This is 1, this is 1, this is 2. And so when you multiply these two zeta function, the only term that remains is the intersection, this area or this volume that both zeta functions are 1. Because 1 times 0 is 0, and 0 times 1 is 0, and you get 1 only if 1 times 1. Right? You get this? Because this intersection represents the fully occupied states for both nk and nk prime. Okay, so you only need to worry about this volume inside the intersection part of these two Fermi spheres, and then you could calculate this intersection. This is nothing but the intersection of these two Fermi spheres. And I assigned you this problem to you as a homework problem. You carry out this calculation, and you show that this is given by this number. Epsilon 2 is given by approximately this value. Okay, so there are many reference books that you could look for solutions and the detailed calculations. For example, this Kittel, the first book, and Ashcroft-Mermiam, and maybe Flansburgh. Okay, so but in any case, what you need to do is to carry out this calculation for the volume of the intersection part between these two Fermi sphere, and then you multiply by this 1 over q square. And you sum over this q. So that's simple. Not as simple as you think, but it is useful to actually define the center of these two spheres and also the angle between this radial direction of the momentum k and the horizontal direction, and you could define the theta between these two vectors, and you only need to calculate this half of the sphere of the intersection part, because by symmetry you only multiply a factor of 2 once you have done this. Okay, and you need to integrate out this volume only between this point and that point that intersect between these vectors and this volume. So you try that. Again, you integrate over the theta between the horizontal direction and this maximum angle here, and this radius part is between this minimum value to this maximum value over here. So you will figure that out. So let's take a short break. When we come back, we will summarize this Hatree-Fock term and how this theory fails. So let's just pay attention to the negative sign, the minus sign in front of this exchange energy. And this is a very important sign because it has physical meaning. So it's not just coincidence that you get a minus sign. The minus sign carries two meanings. It is there because the Pauli principle, or anti-symmetric wave function of fermions or electrons. And because number 1 is this. Number 2, the minus sign, it is the exchange energy. So in perturbation theory, it is usually, and I think it's almost the case, that when you exchange the two particles, and this exchange energy usually is negative, which means that for, say, this fermions, this exchange energy is actually negative. And more physical reason why this negative signs is here is because of this Pauli principle. So let me just illustrate this Pauli principle. Everybody knows Pauli principle. However, what we want to argue here is that these are the electron Coulomb energies, which involve exchanging two electrons near the Fermi surface. So we know very well that if you want to exchange two particles, you get a minus sign. But at the same time, you know that two electron wave functions is actually 0 at the center and distributed mostly away from the center. Okay, so this is the center of these two particles. Say this is plus and minus region of this R2 minus R1. So at 0, you are sitting exactly when these two particles actually collide. When these two electrons are sitting on top of each other, this distance between them is 0. But you know very well that the Pauli principle will exclude such a situation where the two electrons are sitting exactly on the same spot. So the Pauli principle does not allow this to happen. As a result, these two electron wave functions will not center around 0, but spread out away from 0. This is the wave function of the two electrons looks like in real space as functions of R1 minus R2. So they try to avoid each other, right? And you know that when you exchange two electrons, wave functions, you get a minus sign. And this is precisely what it does, because this exchange two electrons, okay? And the fact that this wave function of the two electron system acquired the minus sign is actually consistent with the minus sign here when you calculate the energy. Because the minus sign comes from the Pauli principle, where you exchange two electrons, you get a minus sign wave function. But the minus sign of wave function will actually carry through this calculation so that you get a minus sign in the energy evaluation. Okay, so another argument why there's a minus sign here is precisely from this kind of a two electron wave function and the Pauli principle. It says that remember, the Pauli principle tells you that these two electrons better go away from each other instead of come together, so they would like to avoid each other. Okay, so this kind of keep social distance, right? So this is a social distance between two electrons where this R1 minus R2 is finite, but now 0. And this, if the wave function of the two electrons looks like this, where these two electrons are away from each other, and this is more stable. If you calculate the energy, and you'll get a minus sign, because the minus sign in energy represents the stability of the state. So from statistical mechanics, you know that if you have two states that are competing to be the ground state stay with more negative energy, or a lower energy state is the ground state. And this is the case here when the two electrons are far apart, so the energy is actually reduced, and therefore you get a negative exchange energy. Okay, so compare with the case where these two electrons are really close to each other, and this causes energy. So if you calculate the energy with these two electron wave functions that almost collide, and this energy is actually increased. It's unstable. So from the stability consideration, and this is actually explained everything, because they need to get away from each other to actually minimize the energy to make this state more stable. And the reason why they try to avoid each other is besides because of the Pauli principle. Okay, so this explains why you get minus sign here when you calculate the energy, the exchange energy in this the Fock term, and that is because of the Pauli principle. So that's the remark number one. And another remark, so let me just mark this remark, is the spins. The spin configuration, remember, are all parallel or spin up or spin downs in, within the Hatree-Fock. And this will favors ferromagnetic state as a ground state. So let me just very briefly define what I mean by ferromagnetic order. This means that if you have the extra electrons in the electron configurations of your solid state materials, say there's 1 electrons per site, and all the spins on each side are oriented in such a way that they are all parallel. And the reason why they tend to be parallel with each other is because you have some exchange interactions between the spins on the neighboring site, which we call the spin exchange coupling. But this is another story. So let's just cut the story short. In many materials, solid state materials, you have such a system that all spins are pointing to the same direction in real space, and this is so-called the ferromagnet. So we will introduce such material later, but let me just tell you very simply the definition of this ferromagnet. For example, this iron or cobalt and so on and so forth. So the Hatree-Fock theory excludes the interaction between opposite spin species, and this inevitably favors the ferromagnetic ground state of many metals. So we will estimate this tendency in just a moment. And we know very well that this is wrong because there are not many ferromagnetic metals in nature. But Hatree-Fock theory predicts that many non-magnetic metals within the Hatree-Fock become ferromagnetic metal, which is certainly not right. So let's just try to check the Hatree-Fock predictions by comparing some observables with experiments. So let's take a short break. When we come back, I will just very briefly start the comparison between the Hatree-Fock prediction and the experiments. Well, this is a historic reason. I believe this is simply just a reason why the Hatree-Fock theory excludes the interaction between different spin species is because within such a perturbative expansion, there is no room that the electrons carry different spins could interact. Because as I mentioned already, that this momentum conservation and also the spin should be conserved. So the first leading term out of the Hatree-Fock is the Hatree term and the Fock term, right? The Hatree term is infinity. We sort it in that way. The exchange term or the Fock term is precisely this exchange. And if you consider this exchange term as a leading correction within the perturbative expansion, and you are dead. There's no other way around that this electron carry different spins could interact in the exchange term. Okay? So you may wonder, why do we include, say, higher order terms in perturbative expansion? It's just up to the first term in V, right? So we could just keep expanding this to V squared and V cubic term, and we evaluate this. Sorry, so if you do this, you still cannot make this happen. And the fundamental error that the Hatree-Fock theory made is the following. As I mentioned, the Coulomb interactions, before we screen these Coulomb interactions, it is a long-range Coulomb force, and the long-range Coulomb force in this Q equals 0 limit is divergent. So everything is related to this divergence of the Q equals 0 or small q Coulomb term, but unfortunately the Hatree-Fock considered this Coulomb term just a small perturbation, but it is not. But if we just by brute force consider such a small perturbation, then this is a consequence of this. So there's no way around this mistake. But you may wonder, why did the Hatree-Fock consider other calculation, other approaches? I'm sorry, this is the simplest way you can think of in quantum mechanics, because you know the unperturbed eigenstate exactly, and the only thing that you need to do is to consider this Coulomb term as a small perturbation. So that's the simplest, easiest way you can imagine. There's no other simpler way than this perturbation theory. And that's the history. So you know this progress in the science always starts from the easiest way. And usually the easiest way is always not the correct path. But we should learn a lesson by making the mistakes, and we're not that wrong to assume that Coulomb potential is a small perturbation, and it is wrong only after we found something is wrong. So we're not a fortune teller. We just do whatever we think is the best at this point. So back in 1950s, or I don't know what is the time that they did this calculation, but back then this is the best they can do. And they learned a lesson once they found that there's a huge difference between the prediction and the experiments. So let's check the experiments. So let me just sketch what we will do next time, because we don't have enough time today. So what we will do is to calculate the energy cost to excite a particle-Hall pair near the Fermi surface. Remember that at low temperatures in ordinary metals, we have plenty opportunity to actually excite electrons just within the thin shell of a Fermi sphere and excite this electron to the outer shell and then create such an electron-hole pair as a quasi-particle or electron-hole pair excitations. But this kind of excitation should be cheap, meaning we expect the energy cost to have such a particle-Hall excitation is really small in the low temperature limit. And the reason why this is almost costs nothing to get such excitation, I remember you may have such a exercise homework problem. So imagine that this electron and Hall live precisely at the Fermi surface. Suppose the electron and Hall stay at the Fermi surface. Would they decay? Would they decay? You know the answer. Yes or no? Would they decay if the electrons sit precisely at the Fermi surface? The answer is no. Why? I've shown you already, right? Because the scattering probability is actually proportional to this narrow window, right? This of KBT, and also we need to conserve the momentum energy. Okay, from the energy conservation law, we don't have such a epsilon 3 and epsilon 4, which are the scattered electrons that are out of the Fermi surface, and this violates this energy conservation, because if they are sitting precisely at the Fermi surface, then epsilon 1 and epsilon 2 is just twice as Fermi energy, right? But they cannot be scattered out of the Fermi surface because the two outgoing electrons carry energies at least more than epsilon f. So if you add them up, you get more than 2 times epsilon f, which cannot be conserved. And therefore, there's no way that this electron-hole pair sitting exactly at the Fermi surface will decay. So they live forever. And this is very important point. So these quasi-particles near the Fermi surface actually live very long. And the consequence of this is that it is very easy to create such electron-hole pair. But you'll see next time that when we calculate the energy cost with the Hatree-Fock or exchange energy, that allows us to create such electron-hole pair excitations, and the energy cost is infinity. This is as simple as this. So the energy required to create a particle excitation within the Hatree-Fock is actually infinity. And from this, you know that everything that you calculate, that you can measure it within the Hatree-Fock is actually divergent. Everything is singular. All quantities that you can measure it within, but if you calculate this within the Hatree-Fock, are infinity. So this divergence carries through all observables, and therefore this is the dead end. And the origin of this failure is precisely because of the long-range Coulomb tail, which cannot be small perturbation, right? So I hope you can actually understand the physics behind those mathematics and read the corresponding chapters or sections in the textbook and do the homework. Okay, so I'll see you on next Monday.